Several studies have investigated the impact of multiple motor circuits in a single duct bank. According to NEC Article 310.15 up to 15 motor circuits are permitted in a single duct bank without derating, provided that firstly, the duct bank has a cross-sectional area not less than 6 square inches per circuit. Secondly, the ambient temperature does not exceed 30 degrees Celsius or 86 degrees Fahrenheit. And thirdly, the cables are type MV90, MV105, RHH, RHW, RHW2, or THWN. The Neher McGrath method is used to calculate the ampacity of underground cables, taking into account cable grouping, duct bank configuration, and soil thermal resistivity. When approaching 15 motor circuits in a single duct bank, the ampacity calculations become more complex due to increased heat dissipation. The ampacity of underground cables is affected by several variables, including firstly, cable size and type, secondly, duct bank configuration such as number of cables and spacing, thirdly, soil thermal resistivity, fourthly, ambient temperature, and fifthly, load duration. Several studies have investigated the ampacity of multiple motor circuits in duct banks. These include IEEE paper 824 5534 one investigation of motor circuit derating in duct banks using Neher McGrath method and IEEE paper 15584 4072 7 ampacity of multiple motor feeder cables in duct banks. The studies found that the ampacity of motor circuits in duct banks dera significantly as the number of circuits increases. The derating is more pronounced for smaller duct banks and higher ambient temperatures. Based on the studies, the following recommendations are made. Firstly, limit the number of motor circuits in a single duct bank to less than 15, if possible. Secondly, use a larger duct bank to reduce derating. Thirdly, consider using higher temperature rated cables. And fourthly, perform Neher McGrath calculations for duct banks with more than 10 motor circuits to determine the actual ampacity. While the NEC allows up to 15 motor circuits in a single duct bank without derating, it is generally recommended to limit the number of circuits or use a larger duct bank to ensure adequate ampacity. Neher McGrath calculations should be used for accurate ampacity determination for duct banks with multiple motor circuits. The Neher McGrath method is a mathematical model used to calculate the temperature rise and ampacity of cables buried in the earth or installed in duct banks. It considers several factors, including the heat generated by the cable, the thermal resistance of the cable insulation, the thermal resistance of the surrounding soil, and the ambient temperature of the soil. The method involves solving a series of equations to determine the cable temperature and then using this temperature to calculate the ampacity. The ampacity is the maximum current that the cable can carry without exceeding its temperature rating. Several factors can affect the accuracy of Neher McGrath calculations. These include firstly, the accuracy of the input data, such as the soil thermal resistivity and ambient temperature, secondly, the complexity of the duct bank configuration, and thirdly, the assumptions made in the model. The Neher McGrath method assumes that the heat generated by the cable is uniformly distributed and that the soil is homogeneous. In practice, these assumptions may not always be valid. The ampacity of underground cables is also affected by the type of cable insulation. Cables with higher temperature ratings can carry more current than cables with lower temperature ratings. For example, MV90 cables have a temperature rating of 90 degrees Celsius, while THWN cables have a temperature rating of 75 degrees Celsius in wet locations and 90 degrees Celsius in dry locations. The type of soil surrounding the duct bank can also affect the ampacity of underground cables. Soils with high thermal resistivity can trap heat around the cables, leading to higher temperatures and reduced ampacity. Sandy soils generally have lower thermal resistivity than clay soils. The depth of the duct bank can also affect the ampacity of underground cables. Cables buried deeper in the ground are generally cooler than cables buried closer to the surface. This is because the soil temperature is more stable at greater depths. The spacing between cables in the duct bank can also affect the ampacity of underground cables. Cables that are spaced too closely together can overheat, leading to reduced ampacity. The NEC specifies minimum spacing requirements for cables in duct banks. A load factor of the motor circuits can also affect the ampacity of underground cables. Motor circuits that operate at a high load factor will generate more heat than motor circuits that operate at a low load factor. This can lead to higher cable temperatures and reduced ampacity. The voltage drop in the motor circuits can also affect the ampacity of underground cables. Excessive voltage drop can reduce the motor's performance and cause it to draw more current, which can lead to higher cable temperatures and reduced ampacity. The harmonic content of the motor current can also affect the ampacity of underground cables. Harmonic currents can cause additional heating in the cables, leading to higher temperatures and reduced ampacity. The presence of other utilities in the vicinity of the duct bank can also affect the ampacity of underground cables. For example, underground gas pipelines can increase the soil temperature, which can lead to higher cable temperatures and reduced ampacity. The age of the cables can also affect their ampacity. As cables age, their insulation can degrade, which can lead to higher temperatures and reduced ampacity. It is important to inspect underground cables regularly to ensure that they are in good condition. The NEC requires that underground cables be inspected periodically. The results of the Neher McGrath calculation should be compared to the NEC ampacity tables to ensure that the cables are properly sized. If the calculated ampacity is less than the NEC ampacity, the cable should be upsized. In some cases, it may be necessary to install a larger duct bank to reduce the cable temperatures. A larger duct bank will provide more space for the cables to dissipate heat. It may also be possible to reduce the cable temperatures by using forced air cooling or other methods. Forced air cooling involves blowing air through the duct bank to remove heat. Other methods include using heat pipes or liquid cooling. The cost of these methods should be weighed against the cost of installing a larger duct bank. The decision of whether to limit the number of motor circuits, use a larger duct bank, or use higher temperature rated cables should be based on a cost-benefit analysis. The cost of each option should be compared to the benefits of increased ampacity. In some cases, it may be more cost-effective to limit the number of motor circuits. In other cases, it may be more cost-effective to use a larger duct bank or higher temperature rated cables. The design of underground duct banks should be based on a thorough understanding of the factors that affect cable ampacity. The NEC provides guidance on the design of underground duct banks, but it is important to consider all of the factors that can affect cable ampacity. The Neher McGrath method is a valuable tool for calculating the ampacity of underground cables, but it is important to use the method correctly and to understand its limitations. A qualified electrical engineer should be consulted to design underground duct banks. The electrical engineer will be able to assess the specific conditions at the site and to design a duct bank that meets the needs of the application. The electrical engineer will also be able to perform the Neher McGrath calculations and to ensure that the cables are properly sized. The installation of underground duct banks should be performed by qualified contractors. The contractor should be familiar with the NEC requirements for underground installations. The contractor should also be experienced in the installation of underground cables. The maintenance of underground duct banks should be performed by qualified personnel. The personnel should be trained to inspect underground cables and to identify potential problems. The personnel should also be equipped to repair or replace damaged cables. The safety of personnel working on underground duct banks should be a top priority. Personnel should be trained in the proper safety procedures. Personnel should also be equipped with the proper safety equipment, such as gloves, hard hats, and safety glasses. The use of underground duct banks is an effective way to distribute power in urban areas. Underground duct banks can help to reduce the visual clutter of overhead power lines. Underground duct banks can also help to improve the reliability of the power system. The design and installation of underground duct banks should be performed carefully to ensure that the system is safe and reliable. The NEC provides guidance on the design and installation of underground duct banks. A qualified electrical engineer should be consulted to design and install underground duct banks. The engineer will be able to assess the specific conditions at the site and to design and install a duct bank that meets the needs of the application. The engineer will also be able to ensure that the system is safe and reliable. The information provided in this narration is for general guidance only. It is not a substitute for professional engineering advice. Consult with a qualified electrical engineer for specific design and installation recommendations.